In today's class, we are going to learn about an 8253 and 8254 timer. So 8254 the timer consists of, and in fact 8253 also consists of 3 independent 16-bit programmable counters, and that means within this IC there are 3 16-bit timers which can be programmed. Okay, and each of the counter can independently be programmed for binary or BCD. Okay, so they can be either they're all down counters, and each of them can be programmed for binary counting or for BCD counting. So we need to give an input clock also, so according to that clock it would function. So the clock input is 10 megahertz. Okay, so and each of these 3 timers have independent clock inputs, so the maximum frequency which we can give is 10 megahertz. Okay, so it is useful wherever the microprocessor must control real-time events and all. See, we have also when we have learnt about delays and all, so we have learned that we write a small program to insert delays, like controlling of motors and things like that. We have learnt how to insert delays. But when we insert delays within 8086 program, what happens is the microprocessor is has to execute that program to create that amount of delay, and it cannot do any other function during that time, right? So that is a mere wastage of the 8086 resources. So what we can do is, whenever such delays are required, we can outsource the delay aspect to some other IC. That is, we can tell this IC, okay, now the time starts, and let me know after 10 milliseconds you let me know. So meanwhile the 8086 can go ahead and do other programs, and so that the resources of 8086 is not wasted just to create some delays. Okay, so that is where this becomes very useful. So these timers. Okay, so these two 8254 is just an advanced version of 8253. There are only small differences. One of the 3 differences are listed out here. That 8253 can operate at the maximum of 2.6 megahertz, whereas 8254 you can give a clock up to 10 megahertz. The technology is different. It is NMOS and HMOS, and the most important one down, which is there, the third one, that is we can't read the counter reading on 8253, whereas 8254 at any given time whatever is the count in the counter, that can be read using a read back command. Okay, so that is the advantage of 8254. So now this is the pin diagram of 8253. Okay, and 8254 also. So now whenever henceforth whatever we are going to discuss is applicable to both the ICs. Okay, so this is 8253 IC layout. So if you see, there are 8 pins. Okay, so from D0 to D7. Okay, from D0 to D7, they are the 7 data pins which gets connected with the 8086 to program these 3 counters. So through these data lines we can program these counters. So there are 3 counters. If you see, each counter has got a clock input, like the counters are counter 0, counter 1 and counter 2. So counter 0 has got, if you see pin number 9, it has got a clock input and the gate input and an output here. Okay, output input. Okay, output is an output. This is an output pin available. So how does this counter function is, initially we load the count using the 8 programming through this data lines. We load a 16-bit count whatever into the counter. So the counter starts, and then the counter doesn't start immediately. You have to give a gate signal also. Okay, obviously the clock has to be there. So once you give the gate signal, so the counter would start. Okay, and when the counter becomes 00, the output signal goes high. Okay, so this is just one mode of operation which I am explaining. There are other modes also. We will take on those other modes in the later part of the lecture. Okay, so time being, just understand that there are 3 counters we can load 3 different values in these 3 counters, and we can give 3 different clocks to these counters. We can program these 3 counters independently, and they will all start, they can simultaneously, they will start operating, and then when the count becomes 0, an output is available. So that output can be used as an interrupt signal, and we can tell 8086, okay, this, and we can introduce some delay out here, and at the end of that, this will give a signal to the 8086, okay, this count has completed. So that is how we can introduce delays, and there are other functions of these counters also, we will see. Okay, so this is how these 3 counters work. Okay, from 8086 now also we need to, now since there are 3 counters, and also there is a control register, okay, to program these counters. So there are 2 address lines available, A0 and A1. Obviously 00, you can address this counter whenever we want to send the initialize the counter with some value. You can use 00 this address line, so this counter will be addressed. Okay, these data lines will get connected to this counter, and also when we are we can read the counters also, so there is a read input also. So whenever this read signal goes high from this counter, if it is 00, you can read the data also. Similarly 01 is intended for addressing the counter 1, and 10 for counter 2, and 11 is for the control register. Okay, so with 11 in conjunction with 1, when we are putting 11 out here, right, and then we this control register is selected, and then we can program all these 3 counters using this register, this address, through the control register. There are several control registers. Okay, we'll see how they are addressed individually, and all these counters are can be programmed individually. Okay, so this is how what the layout looks like. Okay, pin diagram of 8253 and 54 looks like. Okay. Now there are some features of 8253 which is listed out here. A clock input is required, which provides a basic operating frequency to the timer. A gate input which controls the timer in many modes. Okay, and an output connection is to be obtained. This is the output of the timer. Okay, so this either goes high or low depending on the mode of operation. Okay, for mode 0, when the count becomes 0, this will go high. Okay, for other modes, and it works differently. We will discuss that. Okay, so this is like we discussed already, 00 and 01, 10 and 11, and also there is a chip select line also. If you see the pin diagram out here, there is a chip select line also, so we need to this. Okay, so this chip select line is also required, so that there could be n number of 8254s which are connected to 8256, so we can use this chip select line. Like we selected the input output devices and the memory devices. Similarly, there could be more than one 8254s connected to 8256, and we can use the chip select line to select the intended 8254. Okay, so these are the features. Okay, now like you with when we are connecting with 8254 with 8086, so there are 2 ways of connecting it. Either you can have A0 and A1 of 8256 connecting directly out here, right? So in this, because there is no odd bank and even bank, nothing like that in this case, right? So because this, each of them is a 16-bit counter, and we'll see how the using only the 7 bits, how the 16 bits are put into this. That we will learn here. So there is nothing known as even bank and odd bank out here, like unlike the memory and input output devices. So you can connect A0 and A1 also. In that case, these addresses would be like for gate it will be 00, 01 and 02, and control line will be 03. Or in some configuration, if you can even connect A1 and A2. right? In that case, if you are going to connect with 8086 A1 and A2, and if you are going to use A0 for chip select, in that case this numbering would be different. So the addresses will be like 0, 0, 0, 2, 4 and 6. Okay, for the gate 1, gate 2, gate 3 and the control register. So accordingly, you just have to know how it will be specified in the question. So accordingly, you will have to note down the address of these different gates and how it is. Okay, so how to program the counters. So initialize each mode of the counter is to be planned, and then we send individual commands for each of the counter. We need to program it separately, each the counters, and that program is done through address and A0 A1 by giving 1 1 into the control register. Okay, once that is done, we send the count value to the counter, to the respective counter. So there we address the particular counter. It could be for counter 0, it has to be 0 0, for 1 0 1 and 2 1 0 accordingly. And this is done at the counter address. Okay, so that is initially load the counter with whatever count we want, and then enable the gate. So each counter has, we said, if you see, each counter has got, if I go back here, it has got a gate input also. So the gate needs to be energized. Okay, once the gate signal goes high, only then the counter would start counting. So after putting the count value, we have the gate signal. So now it starts counting, and then at the end of the count you get an output 0. Okay, so that is what it is. Okay, now this is how the control word format is there. Okay, so the first two MSB bits, okay, that selects the counter, okay, which is the counter to be programmed. Okay, so if I write start with 0 0, then whatever I write here, then the counter 0 will get programmed accordingly, right? So we can push this data control format into A1 three times. Okay, so each time you can change the value of this first 2 bits, and accordingly these counters will get in the first go, the counter 0 will get programmed. If I write 0 1, counter 1 will get programmed, and if I write 1 0 here, the counter 2 will get programmed. Okay, and not necessarily it has to be in the same sequence. You can program any sequence, any counter at any time. Okay, so not necessarily you have to program counter 0 first or counter 1. So you just have to specify which is the counter which you intend to program. Okay, so 0 0. So the first 2 bits stands for the counter. The next 2 bits stands whether it is the first is 0 0 counter latch command. Okay, so time being this enables the count to be latched into a register. Okay, so that we'll discuss after 2 slides. 0 1 means whether it is like it is a 16. I told it is an 16-bit register, right? The counter is a 16-bit and a counter. So you can either feed only the LSB. Okay, if you put 0 1 here, okay, only the least significant bit of the counter, you can write or read information into the only one of the into the lower significant byte only, and obviously the upper significant bit will be 0 in that case. Okay, similarly if you can push in data only to the most significant byte, so in that case the LSB will be 0 in that case, or you can write 1 1, in which you can put in into, you can use both. You can put in 16-bit data into the counter, okay, by using 1 1 out here. So since it is only 8-bit data line, so you will have to write the write operation twice. Okay, in the first write operation, the data will be taken as the LSB, and in the second write operation, the counter will the most significant byte of the counter will get loaded. Okay, through an example I will make these things even more clear. Okay, the next 3 bits indicates the mode of operation. There are total 6 modes, mode 0 to mode 5, right? So we'll see each of those modes in details, but mode 0 is essentially you load a counter and it will down count, and at the end of the count it will give an high signal at the output. Okay, so time being we'll concentrate on mode 1, and then we understand how the control word is written, and subsequently we will take on the other modes also. And the last bit of this control format, if it is 1, it will be BCD, the counter will operate in BCD mode, and if it is 0, it would work in binary mode. Okay, so is this control word format clear to all of you? Anybody has got any doubts here? No? Okay, then we move forward. Okay, so I have inserted just one example here so that things are clear. Suppose we want to program counter 1, okay, for mode 0 operation. Okay, mode 0 operation, I told it is going to be simple down counter. Mode 1 and 2, 3 are going to be complex counters. We'll see that. Okay, so we just now, for time being, we want to, if we want to program counter 1 for mode 0, and then it has to be binary counting, and the value of n which we want to put is 3A98. So this is some count value we want to put here, so that accordingly after when it starts counting from this value, down counting, and when it is 0, it is going to give me a high signal at the output pin. So how do I program this counter? Okay, so if you see, the first is this has to be 0 1, because I am going to program counter 1, so this is become 0 1, and this is 1 1 out here, 1 1, because I have to have, and now I have a 16-bit data which requires to be programmed, so this becomes 1 1, right? Both the MSB and LSB I want to load it, so I have put 1 1 here, right? This is mode 0, so all the 3 has gone 0, so this is binary. Okay, so move AL 70. Okay, now I am writing it, so this is the AL into the AL register. This is 70, right? This is what we have written out here. So that control word 70, and then out 46. Okay, so 46 is the address of the control register. Okay, 46. So out 46 and AL. Right, so we have now programmed, the mode of operation of counter 1. Now we need to, now I told you this could be 43 also, it depends on how the circuit is connected. If 8086, if pins of A0 and A1 is connected to A0 and A1 of 8254, then this will be 43. Okay, so now if you have, now you want to move the first the LSB, that is 98. So you write 98, move AL, and 42. Now 42 corresponds to the address of counter 1. Okay, again, like I said, if A0 and A1 corresponding of 8086 and connected, then this will be 41. So here we are assuming it is the A1 and A2 pins of 8086 is connected, so that is why it is come to 42, otherwise it will be 41. So now you are moving 98 into the first counter 1, and then again you write take the second MSB into the AL register, and you write one more out operation, in which now the MSB will get amended with 3A data. Okay, so this is how we put this data 3A 9A into the counter, and also we have programmed for the mode of operation, and now when the gate signal goes high, the counter will start down reading from 3A 9A towards 0. Okay, so excuse me, this is now if at all we want to load only 98, okay, into the LSB of the counter 1 in the mode 0, in the same mode 0, then what do we do? So in that case, since it is an only LSB, this will become 0 1, right? If you see out here, LSB is only 0 1, so this will become the control word will become 50. Then you write out 40 into the control register only 50. Okay, 50 hexadecimal, that is what we are going to push in. So accordingly it will get programmed. Now you just have to give 98 and out into the register. Okay, so because we are going to give only the LSB data. Similarly, you can also push in only 3A into the MSB of the counter. Okay, if you want to do that, then this will become, these 2 bytes will become 1 0, so which is corresponding to 60H. Control word will become 60 accordingly, and then you write an out command and then move AL 3A, and then now automatically since you have programmed it for MSB, now when I am writing an out command, so whatever is the data which is available in AL register, that goes into the MSB byte of the counter, because you have programmed it accordingly, right? So that is why it will go accordingly, it will go there. So this is how we program these counters. Is this clear to all of you? Is there any doubts? No? Okay, good. Then we'll proceed further. Okay, now reading the counters. Okay, you can always do a simple read operation. Okay, how do we read and do a simple read operation? By a command like in, and then give the address of the counter 1. Okay, and so that the whatever is the data available in counter 1 can come into the AL register, right? So A0, A1, we have 2 pins, A0, A1 to select one of the counters, right? So you can use an in command and read the operations. Okay, but when we if you have a 16-bit data, also if you require both of them, we can write 2 in operations, like we have written 2 out operations for getting these data. Similarly, you can write 2 in operations. In the first in operation, the data from the lower byte will be fetched, and in the second in operation, the data from the higher byte. But when we are doing that, since the counter is running, if you want to read, so you need to stop the counter, otherwise you will find you could find the data which is continuously moving if you are reading at that particular given time, because the clocks may not be the same, right? So even while reading, the data could change and you could get some junk value. So you need to inhibit the counter during that time by either putting the gate signal low or by stopping the clock. Okay, so there are 2 options you can do. Okay, so this is not a wise thing to do. So you have something known as the counter latch command. Okay, so what it does is even once you give a counter latch command, whatever the value of the counter is latched onto a register. Okay, counter latch register. Okay, but the counter will keep continuing moving forward. So once you have given that command counter latch, so whatever at that particular instance, when 8254 receives that signal of counter latch, whatever is the data available on that particular counter will be latched onto a register. Now microprocessor can read that data whenever it wants, not necessarily immediately after that command. It can read after that, and after a few seconds delay, or whenever it wants. The moment it reads that signal, whatever was that data what was captured and stored, that will be available to the 8086, and once the read operation is complete, that latch will go will again start following the counter. Okay, so the data in the latch will be available till the CPU reads that, the 8086 reads that data, or if you have put in some new again you have reprogrammed the counter, even in that case again that the latch normally keeps following the counter. Okay, so the data of the counter will be replicated in that latch. Okay, it will latch on to the data only when you give it a command to latch. Okay, so it will be clear in an example out here. Okay, how is the latch format? Okay, so whenever we want to latch, so the first 2 control bits. Okay, this again the latch command needs to be given into the control register. Okay, so the address will be 11. Okay, and then the first 2 bits for the latch we need to specify the counter. Okay, number. Okay, so it will be 00 for the first counter, or 11 for the second counter, or 02 for the third counter, and once you give those 2 counters, here if you see, instead of here we said these 2 bits initially we were using it for 01 counter, no, these 2 bits, if you say this was for these 3 0 1 1 0 and 1 1 we discussed, it was least significant bit, most significant bit and 16 bit data. Now if you put 0 0 here, that means the counter is going to be latched. Okay, so if I write 0 0 0 0 here, the 0 counter is going to be latched. Okay, this will become don't cares. Okay, now if I write 0 1 0 0, the counter number 1 is going to be latched. Okay, now if I write a 1 0 and 0 0, the second counter data is to be latched. So whenever we send that particular control command, okay, to the control register, at that particular instance, whatever is the value of that counter, that will be latched. Okay, so each counter has got its own different latch. So you can write 3 commands sequentially and latch all the 3 counters also. Not okay, so it is all are independent latches, and you can read them independently whenever you want. Okay, the moment you read it, the counter will the latch will again start following the counter. Okay, so this is how, if you want to latch counter 0, so first we are moving the address of the counter of the control register into DX, and then we are putting all 0 zeros into AL and out DX AL. Okay, by this way we are telling the control register that okay, the counter 0 needs to be latched, so that value of the counter, whatever was the particular count of that counter, that will get latched into a register, but the counter will not stop there, it is continuing, and then whenever we want to read the value, now if you see read, you are not reading it from the control register. Okay, now the data of the counter latch is available in counter 0 only. So if you have when we are accessing it, you have to give the address of the control register. Okay, control 0 register. Okay, move DX and then in AL. So whatever is the data available from the in the latch will be read into the AL register. Okay, so be careful out here. Here we are not giving the control register address, we are giving the address of the counter 0 only we need to give. Okay, so is this clear to all of you? Okay, so this is how we read the counters. Now if you see the problem out here, what was there, that we had to write 3 different commands to latch the output of the 3 different counters. So in 8255, that was the problem with 8253. So in 8254 we have something known as the read back command. So what the read back command does is, using a single command we can latch all the 3 counters at a given time. Okay, the status of all the 3 counters at any given instance can be captured. Okay, so here we are going to use in this case we are going to use the most significant bit as 1 1, right? Okay, so here in the control word, right, for the first 3 control words, if you see here, these are the first 2 control words. We learned till now, we learned 0 0 is for counter 1, 0 1 is for counter 1, and 1 0 is for counter 2. This is, I am speaking about the control word within the control word, right? Now 1 1 means that this is not specific to the counter. 1 1 is something known as a read back command. Okay, so but again, this whole control word we are going to give it to the control register. Okay, so that address will be 1 1. Okay, ending with 1 1. Okay, now so for the read back, when we write 1 1 here, okay, so these are the so this is the 1 1, and this is the rest of the format of the control word. So this will be the first one, will say whether you want, if you put a 0, it means the counter value will be latched on. So if it is if status is 0, then the status is 0, then the status of the counter will be latched on. So each counter will have 2 registers. Okay, one will be count register and one will be status register. Okay, so when we write 1 1, if I write 0 out here, so the count latch will be activated. If I put here D4 is equal to 0, then the status register also will be latch also will be activated. Okay, and then you have 3 bits. So not necessarily all the 3 counters needs to be latched here. So whichever counter you want to be latched, okay, so that need to be given 1 here. If I want all the 3 counters to be latched, I can write 1 1 1, and if I want only counter 2 and counter 1 to be latched, I can write 1 1 0 also. So not necessarily. So this gives an flexibility to us to tell the 8254 which data requires to be latched. Okay, the least significant D0 will always remain 0 in this format. Okay, now we know what is count. That is the count of the register which will get latched as a 16-bit register into a 16-bit register. What is status now? Okay, so what is status? It is a register, and what are the contents of the status register? So this will be the contents of the status register. When we say a read back command, so this data will be captured into the status register. Okay, the first one will be the status of the output. Okay, what is the each of the counter has got an output pin, right? So whatever is the output pin value, that will be captured as D7. Okay, if the null, if the counter is at 0, then this will be 1. If the counter is not 0, it is reading at that particular instance. If the counter is not 0, so this will be a 0. These are the RW1 and RW0. So when we have programmed the counter, okay, we have given, right, 1 0 0 1. These are the combinations which we have given there, right? So whatever, how was the counter programmed? So that data, the present program and the state of the counter, R0, RW1, RW2, and the present mode of the counter, and whether it is mode 0 or mode 1 or mode 5, or whether, and also whether it is doing a BCD count or a binary count. Okay, so that data, this entire 8-bit data will capture the present status of that particular counter. Okay, so this is known as the status register, and whenever we give that read back command, so the present status of the counter will be latched into the status register. Okay, and once we read this data into the 88 memory, again this data will start following the counter. So this, because the counter is continuously moving, right, these data will not move, but the output and the null data will keep changing. So accordingly this will keep following the counter. Okay, so once we take an example, it will be little more clear. Suppose I want count and status, only for counter 0 I need to latch. Okay, so what do I do? So this is the control bit, right? So the first one will be 1 1, right, and then I need both the counter and the status value to be latched. So this is active low, so I have 0 0, right, and then I am only interested in counter 0 data, so I put 0 0 1 here, so 0 0 1 here, 0 here. So this is the control word now, right? It's in binary. So this is the control word. I am going to send it out to okay, to the DX. Okay, DX, we have loaded the address of the control register here. So out DX AL. So accordingly the control register has been told, okay, now this we have programmed this, we have told the control register, okay, this is the read back requirement. Okay, so once we have done that, now we can read. Now if you see, the data lines are only 7, right? Now there are 3. The first input when we take from there, okay, this is the address which is corresponding to the counter 0. So we move the address of the counter 0 into DX, and we write an in command. So in the first in command, the data the status will be fetched. Okay, the status of that counter 0 will be fetched into the AL register, and then you can move it out from AL register, because the next time again when we are fetching the next in command, again the AL will get amended. So if you want to store that data, so it is just moved into some other register, not necessarily into AH, you can move it into any register, and then again you write one more in command. Okay, again from the same counter counter 0, when you do the second in command, now the LSB of the counter, whatever was latched, that would be fetched in. Okay, and then you move it out again from the AL register, and again you do a third in command. When you write, the MSB of the counter will be fetched. So it will be fetched in this order. Okay, first the status, because there's only 7 data lines available, and whereas we have 3 set of data, which is 3 bytes of data which requires to be fetched. One is the status, and one is the LSB, and one is the MSB of the counter. So we can use 3 different in commands. Okay, is it clear to all of you? Okay, so let's move forward. So this is again the same thing which is shown here, the summary in a little more with little bit colors. Okay, only thing which we have not discussed out here, we have discussed this all. Okay, counter 0, read back command we have, and latch counter also we have discussed. We have not discussed about the various modes. Okay, now we'll take on each of these modes again, one each at a time. Okay, so now this is how the programming is done. Each counter is programmed by writing a control word followed by the initial command. The control word allows the programmer to select the counter, mode of operation, and the type of operation. Okay, type of operation, whether we want to read or write, and also it allows us, because we can read from the counter and we can write into the counter. So the control word allows that, and also whether a binary or an BCD count. Okay, so there are 6 modes of operation, 0 to mode 0 to mode 5, right? And each of the modes, clock input will be required, and a gate control will be required, and the out signal will be required. Okay, there are 6 operations. So these are the 6 operations, and we'll see each one of them. The first one is known as interrupt on terminal count. Okay, so this is known as the mode 0 operation. In the mode 0 operation, the out pin would go, out pin goes low when the mode word or a new count is returned. Okay, the moment a new word count is returned out here, the out pin will go low. Okay, and if the clock is applied and gate is equal to 1, the count begins. Okay, so initially the output pin goes low. The moment you have written a new count, the output pin will be low, and if the clock is applied and the gate is equal to 1, okay, the gate has to be 1, only then the count will begin. Okay, now the count stops if gate is equal to 0. Okay, in between, if the gate goes 0, the count would stop. Okay, and resumes if gate is equal to 1. Okay, if the gate is 0 goes 0 for some reason in between, then the count will be paused and it will resumed from where it has stopped again when the gate goes 1. Now if count return is n, then the output will become high after n plus 1 clocks. Okay, now this is because during the first clock it initializes the counter, so we need to neglect that first clock. After that only the count will start decreasing. Okay, during the first clock the data whatever was written, that gets initialized. Okay, so we have to cater for that plus 1 clock. Okay, out remains high till a new count is written. So once this counter becomes 0, right, then the output will go high and it will continue to remain high till a new count is written out there. Okay, so it will again, when a new count is written, if you see the first line, the output pin goes low. Okay, so it continues to remain high. Okay, now after the counter goes to 0 0, the counter will keep continuing reading, like it will go after 0 FF FE, and then this reading will continue as long as the clock is there, and if the gate is 1, this counter will keep moving. Okay, it might reach 0 0 once again, but it doesn't matter. Once it has reached, it will keep completing, it will keep down counting. Okay, so this is the waveform out here, which is shown here. If you see the waveform here, this is the clock. Okay, now once the data is returned here, right? So output is 0 here. So if you have loaded count 4 out here during the first clock, and when the write signal goes high, during the first clock signal nothing happens, and then after that the 4 clock signals, this 4 keeps decreasing, it comes to 0, and then it goes to high value, right? Here we are assuming that the gate signal is high in this first 3 graphs. Okay, a second case is taken here. Now write bar signal is low here. Why is this write bar signal goes low shown here? That is because only when the write bar signal from the 8086 is going low, the new data will be written here. So this write bar signal low is indicating that only the new data is been written into the counter. Okay, so when this is a new data has been written into the counter, and then the counter starts after the first clock, and a counter is starting out here. Now if you see the gate signal out here in this case is going low for some, and then it is going high. So when it is going low here 5 4, and during when it is, since it is low here, it is skipped 1 clock, it is not gone to 3 here. Okay, and again when the gate is going high, the count has resumed. Okay, it will be further clear in this waveform. Okay, here mode 2, this is case 1. Okay, what is the case 1? If you see here, the data has been written. Okay, you understand what is this write bar? This is coming from the 8086, right? So whenever the 8086 goes write bar goes low and the data is placed onto the data bus bar, only then the data will be returned into the clock. So that is this write bar signal. Okay, so this data has been placed out here. Okay, so during the first clock, nothing is happening out here, and then the counter starts after the first this negative clock, nothing happens here. From here it is down counting. So you have written 4, count 4. So at 0 0 0 the output goes high out here. Okay, so this is how the mode 0, this is a case 1 where the data has been fed, the gate is continuously out here, and the output, the moment the data has been written, the output has gone low, and during the first clock cycle, if you see here this blue line, nothing has happened, and from the next clock cycle, so total after the data has been written, after although you have fed 4, after 5 clock cycles the output will go high. Okay, so this is the case 1. Now if I come to case 2 out here, here again the same thing, 4 data has been written here. Okay, and then what is happening, the gate is high, after whenever the counter value is 2 here, the gate goes low out here. In this case it is shown that the gate is going low, and it is remaining low for a few clock cycles, and then it is going high. So what is happening is the counter value is not now decreasing when the gate is low. Again when the gate is going high, it is again resuming the count. So that's why this out has been stretched. Okay, the low signal of the out has been stretched, and it is going high after an delayed time with respect to the case 1 we saw here, because in between here the gate has gone low. So the counter has gone into a pause mode, and it has held with the data which was there in the counter, and then it has resumed the count when the signal has gone high. Okay, is this clear to all of you? Okay, so we take one more case. Here here the out gate is continuously high, but what is happening out here is like when the counter is continuously here changing from 4 3 to decreasing, meanwhile using a read command, write command, you have updated the data of the counter. Okay, so if you have updated the value of the counter, now you have put 4 back into the counter. Now it starts again from 4 3 to 0, right? So while the counter is running, it is possible in mode 0 that you update the value of the counter with a new value, with a new n value. So this need not be again 4, you can put say 10 out here, then after 10 counts it will this output will go here. Okay, here it is again shown the same value has been loaded again once again, not necessarily the same value, you can put any other value, right? So this is not the same thing for all modes of operation. Okay, for different modes of operation, we will see that if you are going to write the operation, it will not get loaded immediately, it will finish the cycle which it is running, and then only it will take the next data which is being returned into the counter. Okay, but for in mode 0, for this specific case, in mode 0, only in this case, immediately whatever when we write, immediately that data will be updated in the counter. Okay, so this is the mode 0 case 3. Okay, so mode 1, we'll see just mode 1, another two similar. In mode 1, what happens is, or if it's time here, I think we'll stop it here. Okay, we have another 5 minutes. Okay, we'll repeat it if it's not a clear mode 1 in the next class. Okay, so in mode 1, it is known as then retriggerable one shot. Okay, in the mode 1, what happens is, whenever we put the gate signal high, okay, the positive edge of the gate signal, okay, the output would go low. Okay, initially the output will be high in this case. Whenever the gate signal goes high, it is an edge triggered. Now, it need not be continuously high also. Only the edge triggered gate input signal, when it is going high, the counter will start down counting. Okay, and the output would be low during that time. Okay, initially the output will be high, and that is the difference here. There are two differences out here with respect to mode. First, initially the output will be high. Second, it is the trigger need not be continuously high. It is edge triggered. Okay, you just give an edge signal, gate signal from 0 to high, the edge trigger. So it will get activated. So it will keep moving out here. Okay, the third difference out here is, so you have the first edge, the counter will start 4, 3, 2, 1. If you have the second edge coming in before completion of the count, okay, again it will start from 4, 3, 2, 1. Okay, it will start from the value which you have loaded initially. So these are the differences. Okay, that in the 3 cases, we will see the 3 cases, then it will be very clear. So initially we have loaded and data 4 out here. Okay, and now you are giving an edge triggered signal. Okay, gate signal is you are giving an gate signal out here. So once you have given a gate signal out here, so now once you have fed the data also, the output will become 1 here. Okay, in the previous case the output used to be 0 when you load the data. In this case, when you load the data, the output will go 1, and once you get a gate signal, edge, only an edge is required here. So once a signal, you require a small gate signal, the counter will will start down counting, and when it goes to 0, again it will go to high value. Okay, again you get a next gate signal, again it will get triggered to a low value. So this continues. Okay, now in case 2 here, now you have an gate signal coming here, right? That this we just discussed in the first slide also. So you have a gate signal coming here, the counter gets triggered, you have put in data, so it starts running from 4, 3, 2, 1 here. Now it is not reached 0, you have another gate signal coming here, right? Only an edge, positive going edge. So the moment a new trigger has come here, it will again start counting from 4, 3, 2, 0, it will start going, and now it goes to 0. So this is known as a retriggerable. Okay, that means once a trigger is there, even before completion, if you get a new trigger, it will take this as a new trigger, and it will start the count again from 4. Okay, and we have the last case here, in which here it is again the same thing. You have, this is the first gate signal shown here, this is the second gate signal shown here. So in the first gate signal it will go low here, again in the second gate signal it will start a count here, right? And now this dotted line shows in case the gate is coming like this till here. Okay, so then and then but still it doesn't really affect, because it is an edge triggered signal. Okay, so this is not an level triggered, so that is why it is indicated like this. So this particular dotted line really doesn't affect the mode 1 of operation, because it is only the edge which matters. Okay, so if this is going, this gate is continuing to remain till the counter comes to 0, so that really doesn't affect the output out here, because it is an edge triggered. So that is why it is shown here. right? So this is again the mode of operation, the final slide, where you have an gate signal. So it goes low here and it goes out here, and this is the dotted line is shown here. In case you have one more gate signal in before the completion of the count, in this case the initial count is 5. So in case there is an trigger which comes before the completion, then again it will count for another 5 here. So this dotted line is shown here. Okay, so with this we have just discussed mode 0 and mode 1. So rest of the modes we will discuss in the next class. Is there any doubts? No? Okay, then thanks.